All right, diffraction gratings, prob number 7, the last one on the worksheet. We have white light containing the wavelengths 400 to 700 nanometers. That is the range of the visible spectrum. Turns out this is violet to red, or red, the longest wavelength, violet, the shortest wavelength in the visible spectrum. Falls on a grating with 7,500 lines per centimeter. How wide is the first order spectrum on a screen? That's 2.3 meters away. That's the problem. All right, well, so we have the diffraction grating right here, and I'll draw a dotted line here to the screen. Here's the screen. This is 2.3 meters. That's the distance to the screen. And we have the light, it's white light, coming into this diffraction grating. Therefore, there'll be a bright spot of white light right here. And then we have the spread of the light. In other words, all the wavelengths are constructive interference right at the center of the screen. Then the different wavelengths get spread out because there's constructive interference at different places. So the big picture of this problem is we're going to have constructive interference here with one of the, either the shortest or the longest wavelength, right? And then another region right here that is either the longest or shortest, okay, depending. And in this region, there's going to be all the colors of the spectrum. And I'm asking you to find basically this delta y. We're going to find delta y. We're going to have to come up with theta 1 and also theta 2. When we have those two angles, then we can use geometry. Actually, you know what we can use? This is a right triangle. So the tangent of theta, either of these thetas, is equal to opposite. Let me go like this, just to be real clear. y1, and whoop, up here is y2. So for any particular y, the tangent to this angle is y over, well, d, big D. This is equal to big D. So that's what we're going to do. We're going to have to take these two angles, get the y for both of them, and then delta y will be equal to y2 minus y1. So that's what we need to solve for. We need to solve for these y values. We'll plug it into, y is equal to d tangent of theta, which is 2.3 tangent of theta, to get our two values of y. So our task now before us, presented to us, is to discover the value of the y's. And to do that, we're going to, actually what we need to do is find the angles, because once we have the angles, the y's will fall into place here. So we use d sine of theta is equal to m lambda, and what we want to extract out of here is we want to get the two angles. So sine of theta is equal to, now it's first order, so m is equal to 1, so it's just lambda over d. There we go. So we do that for both of the angles in question, and we'll have our solution quite readily. Well, what's d? Well, we have 7,500 lines per centimeter. Now notice lines per centimeter. That's not what we want. We want how many centimeters per line. Therefore, the number of centimeters per line is equal to the inverse of that, 1 over 7,500, which if you plug it into the calculator is 1.33 times 10 to the negative 4th centimeters, which is 1.33 times 10 to the negative 6 meters. I like to keep everything, convert everything to meters, just to be consistent. Might be kind of hard to see that. That's negative 6, which is 1.33 micrometers. There we go. So that is the spacing between the slits in the diffraction grating. So now, sine of theta 1 is equal to lambda over d. We will use the 400 nanometers for that one. So 400 times 10 to the negative 9. That's how many meters. That's the lambda. The d is 1.33 times 10 to the minus 6. That many, 1.33 micrometers. That gives, let's see, 400 negative 9 divided by 1.33 exponent to the negative 6. Whoop, messed up. 400 negative 9 divided by 1.33 e to the negative 6, which is 0.30. Sine of theta 2 is equal to 750 times 10 to the negative 9 over 1.33 times 10 to the negative 6. 750. Gives us 0.56. So really I could stop the problem at this point, but I'll go ahead and finish it off just in case you want to validate. So here we have theta 1. Theta 1 is equal to inverse sine of 0.3, which is, which is 17.5 degrees. Theta 2 is equal to the inverse sine of 0.56, which is okay, operate the calculator. There, which is 34 degrees. All right. So we have those two angles, and now from that we can get our y values. So y1, going back to this again, y1 is equal to 2.3 tangent of 17.5 degrees. 2.3 tangent of 17.5 is equal to 0.72, well, 0.725 meters. Y2 is equal to 2.3 tangent of 34 degrees, which is 1.55 meters. Therefore, delta y is equal to 1.55 minus 0.725, which is equal to 0.83 meters, which is equal to, well, 84 centimeters. 83 centimeters. I don't know, got 84 on my worksheet, but that's just rounding errors apparently. Okay, so there you go. And now the other question is, which one appears first on the spectrum? Well, we see that theta 1 is the smaller angle, so that would be the one that appears first. Okay? And then we move on to the one that appears last, which is the larger angle. Well, this was the red. This was the violet, because violet is the shorter wavelength. In other words, the shorter wavelength appears first, the longer wavelength appears last. So that's the order for the colors. So there you go. Kind of a lengthy solution, but it may answer a lot of questions about other problems on this worksheet as well, if you can do that one. So hopefully that helped.